Hello, welcome to the lecture number 21 of the course Quantum Mechanics and Molecular Spectroscopy. We will have a quick recap of the previous lecture and proceed with the present lecture. In the last lecture, I was talking about rates of emission and absorption and their coefficients. Okay. So, when you have state 1 and 2, okay, there is an absorption and absorption happens in the presence of a H nu, and there are two kinds of emission. Okay. One that happens in the presence of H nu is called stimulated emission, okay, and one this happens in presence of H nu, and there is a spontaneous emission. Which happens in the absence of H nu. Okay. Now we have the coefficients or rate constants, and this is called B, this is also called B, and this is A. And using our transient moment integral or transient dipole moment, we figured out the relationship between AB and also A and the transient moment integral. So, the final equations that we came in the last lecture was A B equals to pi by 6 epsilon naught h bar square transition moment integral F mu z dot electric field along the z axis I, or this could square, or equivalently one could write pi 6 epsilon naught h bar square 2 mu z along the electric field of 1 whole square, and A was nothing but 8 pi h nu cube c cube into B. So, this will turn out to be pi by 6 epsilon naught h bar square into 8 pi h nu cube by c cube into 2 mu z along some electric vector 1 whole square. Now, this is nothing but 2 pi mu cube divided by 3 epsilon naught h bar c cube modulus of 2 mu z electric field vector 1 whole square. So, this is A. Now, we also said that both A and B are proportional to this transient dipole. Okay. Now, one of the most interesting part of spectroscopy using this methodology is that you can get both A and B theoretically as well as experimentally. Okay. One can measure A and B experimentally and calculate theoretically, and one can compare, okay, the experiment and theory, and that is a real test of quantum mechanics. Okay. Now, for example, let us suppose there is a there are two states 1 and 2. Initially there is a population of n1 at time t is equal to 0, okay, something I do not know, some value, and there is n2 at time t is equal to 0. But if you start with a separation of very large separation of 1 and 2, then you can see that n2 0 will be equal to 0, and let us call this as 100%, okay, and 0%, something like that. Okay. And then what you do is you shine light at some point of time, you shine light h nu corresponding to delta E, that is equal to E1 E2 minus E1. Then what will happen? You will transfer some population. Okay. Let us say some population x% has been moved to the x side. So what you get is at time t, this will be 100 minus x, and n2 of t will be equal to x. Okay. Now after that you switch off the light. Now of course the molecules will not be able to stay there in N2 for all the while, because thermodynamically N1 is the most stable state. So the molecules must return to N1 state. So the kinetics of that will be minus dN2 by dt, okay, is going to be proportional to N2, and this is happening in the absence of any light. So the proportionality constant must be equal to the A coefficient. So that is A. Okay. So I can rewrite this equation, okay, and it turns out that N2 of t, it is a simple first order differential equation which you can solve, and you get that N2 of t is equal to 0 is equal to N2 at, okay. Now I am going to use N2 at t prime, okay, exponential minus A times t. Now what is N2 at t prime? N2 at t prime is actually equal to x, that is when the light interaction is complete. So if you switch on the light and wait for a while, and t prime is the state when you switch off the light, or interaction is complete, or when you switch off the light. T prime is the time when light is switched off. Okay. So what you will get is this equation. Okay. Now this is an exponential, you can see this. So what it does is the following. So you can think of it like this: time in N2 of t. So it will have some value and then it exponentially decays. Okay. Now that is, this value will be nothing but N2 of t prime. Okay. It starts at t prime because that is when, and it goes to infinity, and this is asymptotically going to 0. Okay. Now if you have that, this is the first order equation. So your rate constant will be A. So A is the rate constant. Now if A is the rate constant, 1 by A is called lifetime. Okay, we will just come to that. So let us just look at the first order kinetics. Okay. So if you have a population that decays exponentially, okay. So this is, let us say this is N2 of t versus t, and this is N2 of t prime, and I am starting time at t prime. Okay. Now if it is exponentially decay, I told you that the rate constant is equal to A, and the equation is this: N2 of t is equal to n2 of t prime exponentials minus a t. Now let us assume one thing. So when t equals to a, when t equals to say 1 by a, okay, t is equal to 1 by a, and this I will call it as tau. So when t is equal to tau, okay, its value is 1 by a. Then what happens? Then you will have 1 2 into t is equal to n2 t prime. Okay. This will become a into 1 by a, so that will become that will become minus 1. So this will be e to the power of minus 1. So this is equal to 1 by e. Okay. So this is called lifetime. Lifetime is when lifetime is a time, tau is called lifetime, and lifetime is a time when initial population n2 of t prime, okay, decreases to 1 over e of n2 of t prime. Okay. So if you look at that, so for a given exponential the lifetime is fixed, that is 1 over e. Okay. And the rate constant, okay, in this case the rate constant is equal to a, therefore lifetime will be equal to 1 over a. Okay. So it is also called radiative lifetime, tau equals to, so tau now equals to 1 by a, this is equal to, now what is a equal to? A was equal to some constants multiplied by the transition moment integral or transition dipole square. Okay. So some constants, okay, multiplied by 1 over 2 mu z 1 whole square. So one can think of the radiative lifetime tau is proportional to, because these are all constants, 1 over 2 mu z 1 square. Okay. So what is that? So lifetime of the excited state in this case that is 2 is inversely proportional to the transition dipole square. Okay. So what does it really mean? It means that if you measure the lifetime tau, that is inversely proportional to 1 over 2 that means if this number is large, this number will be small. So lifetime is inversely proportional to transition dipole moment. So if there is a transition, strong transitions, have smaller lifetime. Okay. So something absorbs very strongly, okay, will have a shorter lifetime. Okay. This is something that, now if you quickly remember in the chemistry there is something called potassium dichromate, it is very strongly absorbing, okay, because the extinction coefficient is much stronger. So if you excite potassium dichromate, it must decay much faster, that is what it means. Okay. Now this kind of tells you that once you, but by the way, the tau, this value can be independently measured. Can be measured experimentally. This is measured experimentally, which means now this tau of course is multiplied by lot of constants. Okay. But there is another factor that is also important, is that A has this nu cube. So, tau is also proportional to 1 over nu cube, okay, 1 over nu cube into 2 mu z epsilon 1 square. Now, if this value is equal, let us say there are two transitions on molecule A and molecule B, such that, okay, so that I will call it as 1A, 2A, 1B, 2B, and you see this the way I have drawn is this h nu A and this is h nu B, such that h nu A is greater than h nu B. And it so happens that this integral, okay, 2 mu z 1 square of A is equal to modulus of 2 mu z 1 of square of B. If the transition dipole square in both cases in A and B, if they are equal, okay, let's assume a scenario when these two are equal, then what happens is that then your lifetime will depend on 1 over nu cube. That means larger separation, the decay will be the faster. Okay. So, the tau is 1 over nu cube, because nu is larger in the case of A with respect to B, 1 over nu cube will be smaller. Therefore, tau, so based on this one can write tau A will be smaller than tau B, and the ratio of tau A to tau B will be equal to nu P cube by nu A cube. Okay. So, that is only when these two transition dipoles are equal. Of course, if they are not equal, then it will be complex mixture of the ratio of the transition dipole squares and the nu cube. Okay. So, this is kind of a way one can estimate. So, if tau can be experimentally measured, then depending on where you have excited what is the nu, then one can actually experimentally calculate or estimate transition dipole. Okay. Now, what I am trying to say, if tau is experimentally measured, okay, if tau is experimentally measured, then from this one can estimate transition dipole, or other way around, if one calculate using theory transition dipole, then from here one can estimate tau, and then of course this tau is lifetime. So, one can go back and forth. Okay. If you can measure one, then you can estimate the other one, or if you can calculate the transition dipole, you can estimate the tau, and one can go back and forth and see whether you have done it in a very consistent manner. Okay. So, both experimentally and theoretically the transition dipole and the lifetimes can be measured or estimated. So, that is the connection between the transition dipole and the lifetime, and this comes via the Einstein coefficient A. But once you know that Einstein coefficient A, you also know the Einstein coefficient B, because A and B are connected. So, it just takes one experiment to estimate all the values. Okay. So, if I can measure the lifetime, then if I can measure tau, then I can estimate 1 transition dipole, 2 A coefficient, and 3 P coefficient. Okay. So, I am going to stop it here and we will continue in the next lecture. Thank you.